Hey there, Acro University members. Thanks for joining us. My name's Neil. I'm coming to you from Atlanta in our headquarters here. I'm in our applications lab in front of the AXP 2.0, surrounded by our various thermal warpage and room temperature warpage tools. Here to talk on an introduction to warpage. So this will not be a training video or a comprehensive look at the technologies. This is more of an overview or someone new to the technology to take a look at what's warpage, what is thermal warpage, and how might you go about measuring it. So let's get right into it. We'll start by talking about what causes warpage and where it comes from.
So we should start thinking about warpage really just at room temperature first, because the products that you may be working with or get will have shape to them of some sort, and that can come from their production process. But when we get into testing the samples that you may have in-house, then thermal warpage, that really comes from the mismatch of the expansion rates in the materials. So CTE is coefficient of thermal expansion. Something like a die in a package is going to expand at a lower rate than the mold and the substrate layers, and when those expand at different rates, you're going to get shape change in the vertical direction. And then when warpage and thermal warpage occurs, depending on when in the profile it happens, you can have these types of surface mount defects like an open or bridge, or something more subtle like a head and pillow where the sample may pass electrical tests but then fail later in the field.
Okay, so today we have a bare PCB setup in our AXP 2.0. As you can see here, you can see the PCB actually inside of our oven. You'll also be able to see it here on our screen. So the AXP 2.0, to do a quick equipment overview, we have our optics above, we have the oven here, we have motion systems on the sides, and all of our cooling mechanics are down below the tool. So here on the screen, you will be able to see a live view of our actual PCB. You can see my hand moving there, and then if we quickly take an image, the patterns created by our shadow array technology are going to shift and give us a rendering of that PCB surface. In this case, I've taken the global warpage as well as looked at one local area on the board. All right, so we'll take a look at what this does as we heat it now. All right, let's take a live look in here. I've made a temperature profile to use for this run. This is emulating a reflow profile, which is a common use of our tool. We also will recreate reliability profiles or any really thermal excursion that you want to create. But the system just took an image. We're going up to reflow temperatures and capturing the shape of this board as it heats and will here soon cool. So we started around 600 microns. We're now near 1600 microns in shape, so the board is warping. We're hitting peak temperature now, and our cooling process, will start as that occurs. You can hear the fans start to kick on. So we'll check on this as the profile ends. All right, so our profile just ended. We got through a reflow process, took like about 13 images through that. You can really take as many as you want. All of this is programmed in Acrometric software. The input profile, this thermal profiling, and then the analysis package is really where a lot of the complexity and the meat and the value comes with warpage. So here you have the excursion over temperature. You can see the board actually kind of popped and really changed actually on the cool down. We're now at 2.8 millimeters or 2800 microns, so it actually drastically changed shape in kind of potato chip. That does happen at times. And you can see the local area also started to get somewhat of a shadow shape as well. So all this data is saved. You can look at it live here in this software, but most often you're going to take the files that we just created and we'll go and we'll process it. So we can take a look at that after we take a look at the DFP technology, which we'll do right now. A little bit of movie magic here. We now have the DFP inside the system. We also have a wardrobe change because we're busy here at Acrometrics and your customers do call. So now the DFP in, I'm going to take a quick measurement with that. The DFP setup is also inside of our AXP2. Instead of using the optics above for shadow array, we've taken out the grating. We have a projector and camera inside. This takes about 10 minutes to do this actual swap as with most of our modules. So the projection light you can see with my hand, maybe there in blue, the camera above, and you can somewhat see the samples down in there with the blue light. Our acquisition cycle is only about a second with DFP. It's quite fast. In this case, it's going to take a little bit longer to process because it's more data. That's one of the advantages of DFP. But what you get here, I have an actual bald BGA, and you're actually going to get the solder balls. And we'll look at this later and how you might process this data, because as it is, it's not that usable. I mean, it's cool looking, but what do you do with that information? We need to do something with it besides saying, hey, that's 620 microns of warpage. So this is an application where we use DFP. We can make a whole video on DFP versus Shadow Array. The short version is Shadow Array. It's very robust. It's very accurate across a wide range. If you can use Shadow Array, you generally want to. If you have discontinuous surfaces, sudden height change, a connector, things like that, a bulb BGA, DFP is going to be your better answer. It handles the step heights and it has better data density to it, but it's a projector, so if you zoom that projector out, which you can here, that accuracy is generally going to get worse as the projection gets larger. So we'll look more at processing now. How do we take this data and work with it?
Now that we've seen the system in action, let's take a quick look at the software that really drives all of this functionality. So we'll start here with the profile generator software. This is the software to create an input temperature profile to pass to the other softwares and have the oven and cooling systems emulate your real world conditions. So this is a profile in time and temperature in the Y dimension where you can really time it out however you wish. Add in actual acquisitions that you want to take, as well as different cooling functions. You can add in different thermal commands. There's a wide range of actions that the system can automate and reproduce with this software. So we'll take the file from Profile Generator, and then we're going to use it next in the Thermal Profiler software. The next step in the software is surface measurement. This is where you're going to come in, you're actually going to interface with the equipment, where you take your measurements, you set up your tests, and you control the different system variables. You can also do a lot of the processing steps up front or later in surface analysis where you'll show. So you'll control brightness, get your test set up, and then if you want to run over temperature, similarly you're going to have an interface with Thermal Profiler. Now you've already seen this with the live equipment. You saw me using these two softwares, so I'll keep this brief, but essentially you load in the profile that we create in Profile Generator. You see the tabular data as it goes. You get a live view of the sample, and then your results will start to form below. Alright, so we have our data now, and we can bring that into surface analysis. This is the major analysis package where we can look at all the data that we took. So I have just a single example here of our local PCB area. We can take a quick rendering. We can look at it closely. There's a lot of surface roughness, so we can come in and smooth that. That's probably a better representation of how a BGA would attach to that area. And at the end of the day, you're going to take those files that were created and you're going to batch process them and then look at essentially reports, so statistical information. So batch processing interface, there's a lot to see here. Again, this is not an explanation of how the tool is used. You load in the files and then kind of a reporting interface, so you can create at the end of the day a report to look through and see what this board did over temperature, either through gauge information and statistics or through 3D renderings to show you kind of what happened. You can do gauge plots, local areas. We can look at the PCB local, as we did before, get diagonals of that. That's what a lot of your output at the end of the day is going to be. And this can be done on very, very large quantities of data and then looked at statistically as well. So we still need to look at our DFP data, and we'll also look at how you might compare these two data sets together. Going back into surface analysis now, so here's our DFP data from our BGA, and we've actually used a function called feature detection to locate these balls in space. As we discussed, the the BGA with balls, while it is an interesting data set, if you're going to look at it for warpage, the balls are really going to be almost all of your height. So this is a software we've built in, and I won't show the full use, that's used to automatically locate those balls, and then we could exclude them from the data set and get just the substrate data, kind of as you see here in the underlying substrate. Or we could do something with the ball peaks, in this case, like actually pulling out the highest point of each individual sphere and plotting that. If we want to compare these data sets, we can also do that within the software. Say we want to look at the PCB and compare it to the BGA substrate. That can be done in interface analysis, and this is a software that's actually kind of being overhauled right now. You see there's actually a version of it within surface analysis. This used to be, or traditionally was, a separate application. But this is really the more important data at the end of the day, is how these gaps are between these two attaching surfaces, and then what might happen to them as temperature changes. So these variables are really critical for your warpage analysis, for attachment of your packages, over temperature, and how these surfaces will interact with heat and shape.
All right, thanks for hanging out with us. This is Neil from the Acrometrics headquarters here in Atlanta. It's been your intro to warpage, and we'll see you next time.
To find out more about minimizing warpage risk in electronic assemblies, visit acrometrics.com or contact Mark Venko directly. Call 770-480-6604 or email mvenco@acrometrics.com.